Hello everyone, my name is Wei-Shang Wang. I'll be talking about NAT Traversal Mechanism for Media Control by RTSP. Here are some of the acronyms I'll be used throughout the slides. Real-time Streaming Protocol, Network Address Translation, Session Traversal Utilities for NAT, Traversal using relays around NAT, Interactive Connectivity Establishment. Real-time Streaming Protocol is a protocol used in video streaming over a computer network. RTSP allows the establishment of a connection between the client's receiver and the media server that contains the media content. After the establishment of a connection, the protocol is also used to control the media in terms of when the media is played, paused, stopped. When it is time to transfer the media content itself, another protocol will be used since RTSP only deals with the connection and controls. However, when the users of RTSP are behind a router that uses NAT, then the RTSP will have issues with the establishment of the connection. In order to avoid these issues, a NAT traversal will need to be used. In the paper titled NAT Traversal Mechanism for Media Control by RTSP, a new method of NAT traversal is suggested to resolve the issues of allowing users to use RTSP even when the router running NAT is being used. The suggested traversal method is based on Interactive Connectivity Establishment that uses the RTSP 2.0 extension. ICE can be seen as a general NAT traversal method that allows a data connection to be established regardless of the type of NAT being used. Security concerns related to the RTSP protocol is also addressed with the use of ICE. Therefore, the incorporation of ICE into the RTSP protocol allows for a more usable, reliable, and secure connection between the users and the media servers. NAT allows multiple users within the network to all share one public IP address. Public IP addresses sometimes need to be shared because there are constantly new devices being connected to the internet, and the number of available public IP addresses are beginning to run out. NAT works by mapping a private IP address with a public IP address along with a port number. This mapping only takes place when the client connects to the known public IP address. When the response message is received, the mapping is used to determine which private IP address to send the data to. There are 4 different types of NAT. There are focal NAT, address-restricted code NAT, port-restricted code NAT, and symmetric NAT. Focal NAT allows any external IP address to use the NAT mapping that currently exists in the table regardless of who caused the entry in the table. An example would be, let's say my PC has a website running on port 80. I create a one-to-one rule that maps my router 1 IP of 1.1.1.1 to my local IP address with the port 80 to port 80. Any external host that sends data to my public IP address on port 80 is netted to my local IP on port 80. Any connections attempt on any other port is dropped. Address-restricted code NAT is similar to full code NAT, except it will only allow an external address to use the mapping of the client previously connected with that other external address. An example would be, let's say my computer makes an outbound connection to a website 22222 with my IP, local IP, and port 12345. NAT creates mapping to my PC using the port 12345. So then the packets that arrive with the source IP 2222 using the destination port 12345 will only be accepted and sent to my PC. Any different IP and port number will be dropped. Port-restricted code NAT will also allow any previously reached address to use the NAT mapping, except when the external host must be using the same source port as it originally was using when it first reached the client. An example would be, let's say my PC makes the outbound connection to website 4567 on port 80, which is a destination port. The NAT maps my source IP, my local IP, to one IP of 2222 and the source port of 12345. When the website sends packets back, it must have its source IP as 4567 and its destination port as my port, which is 12345, with addition of its source port as 80. If any of the 3 are different, then the NAT will drop the connection. Finally, symmetric NAT will only allow the mappings in the table to be used by the original destination address when they respond back to the original request. An example would be, let's say my PC makes two outbound connections to 1111 and 2222 with private IP and port number 12345 for both connections. The symmetric NAT changes the port 1 for one connection, 2 for the other connection, and these port numbers are generated randomly, so then it creates a unique mapping. So to create a unique mapping for each connection, and traffic from those destinations must come in on the respective port. So 1 must send the package to port 1, on the other hand 2 must send the package to port 2. Packets sent to any other port will be dropped. NAT mapping only takes place when the client initiates the connection. Therefore, depending on which of the four types of NAT is being used, any client that uses NAT cannot be initially reached from the outside network unless there's already a mapping that exists for the outside host to use. This property causes many issues with a certain type of protocol. Protocols that use incur these issues deal with sending data from one peer to another. The reason for this is due to peers not having the known static IP address and one or more of the peer being behind a NAT. Example of this protocol including Session Initiation Protocol used for voice IP application and real-time streaming protocol used for controlling media streaming. Another issue with the NAT arises when the data contained in the payload of the packet is sent through the NAT. Since NAT only looks at the IP address and port numbers located in the packet header field, any IP address information that is placed in the payload will not be changed during the mapping processes. This will cause the client to place its local IP address in the payload, and when the receiver tries to use the address, it will not be able to reach the sending client. This downside of using NAT has many solutions, but none are perfect. Stun and turn are techniques that allows one or more peers that are behind a NAT to communicate with each other and therefore traverse each other's NAT. Session traversal utilities for NAT, also known as stun, works by allowing the client to discover its public IP address even when the client is behind a NAT. This is accomplished by having the client contact a stun server. The server will then receive a packet with the client's public IP address. This information is then given back to the client. The client will be able to use this newly obtained information and place it into the payload instead of using its private IP address, which is usually not usable by the receiver. This method also has the added benefit of a NAT mapping entry being created and inserted into the table when the client contacts a stun server. The stun server also determines the source port and relay that information back to the client. The same entry will then use for the NAT traversal if the NAT is being set to full cone. If the NAT is not being set to the full cone mode, then the method will not work. These various NAT settings change the security provided by the NAT, where full cone can be seen as the least restrictive and symmetric being the most restrictive. Traversal using relays around NAT works similar to a stun server in that it will provide the client with the IP address and port this receiver can send the data to. However, this IP address and port number is not the client's public IP address. Instead, it is the IP address and port of the turn server. When the client provides this information to the receiver will then send its data to the turn server where it is relayed back to the client. Turn method is costly because it requires the turn server to relay the data back to the client, so hardware and bandwidth will need to be taken into consideration. There will also be added latency time since there is an additional server and data must travel through before it reaches the destination. Interactive connectivity establishment is a combination of the two NAT traversal solutions. It combines both stun and turn. ICE will first gather its client's IP address. If the client has multiple interfaces, each with its own IP address, then each IP address will be gathered into a list. Then it will contact the stun server and also insert the return address onto the list. Finally, ICE will contact the turn server and insert the return IP address onto the list too. Each item on the list of the IP address is considered as a candidate. Each candidate will also have an associated priority, which is dependent on the user's setting. One by one, starting with the highest priority, each candidate will be attempted to be used. Usually, if a client is directly connected to the internet without a NAT, then the IP address gathered directly from the client's interfaces will work. If that fails, then IP address gathered using stun is used next. If the method fails, then ICE will resort to the more costly IP address gathered using the turn method. The setup of an RTSP connection is relatively simple. The client will look at the session description given it by the server. Based on this information, the client will know what type of media sources it will need to establish on its end of the connection. Next, a seller request will need to be sent by the client. It is required that at least one seller request to be sent by the client. If the client wants to initiate multiple media streams at the same time, the seller request will need to be sent for each of the media streams. When the RTSP server obtains a seller request from the client then begins to determine the request data, resource, and its availability. The server will also look to see various transport methods the client supports. The transport method along with the client's candidate list will result in being able to determine the exact media protocol that is allowed to be used. The RTSP server response is sent upon completion of the setup request. This request can be either an OK response or an error code. When the server response is sent, a transport specification must have already been selected. The selection will need to be included in the server response along with the selected candidate, ICE username, and ICE password. An error must be provided to the client if there is no valid candidate in the list. After this, a connection between the server and the client will need to be checked to determine if the connection is established and usable. Media servers often use proxies for reasons like load balancing, security, increasing performance, or reducing bandwidth. When proxies are used within RTSP servers, the proxies must also support ICE and all of its features in order for the NAT traversal process to take place. This proxy will need to act as both the receiving peer and the sending peer. The proxy becomes a receiving peer when it is communicating with the RTSP server. The proxy will then take on a sending peer role when it's sending the data to the client. The two most common type of proxy used with RTSP servers are media handling proxies and signaling proxies. Media handling proxies will either cache the media data or relay it. Signaling proxies does not deal with the media data. Instead, it only deals with the RTSP signal, so there must be a working NAT traversal between the client and the RTSP server. Security is always a concern when dealing with the protocols that run over the internet, since poorly designed protocols can allow attackers to intercept data or use companies' computing resources to attack another system. When dealing with RTSP, one of the main security concerns will be when the RTSP server delivers a string of media to the receiving client who did not request the stream. Usually, this would not be an issue if the host is behind a NAT or firewall because those unrequested media stream packets would just be ignored and the ICMP message would be sent back letting the sender know that the port was unreachable. However, an issue arises when the attacker repeatedly sends an RTSP request to our RTSP server with the victim's IP address and the destination of the media stream. The victim will constantly be by sending those ICMP error messages for each of the packets the victim is receiving in the media stream. The victim will not be able to receive legitimate traffic, and this is known as denial of service attack. The incorporation of ICE into RTSP deals with many of the security concerns. ICE require connectivity check on the client side. These checks allow the RTSP server to know for certain the client wanted to receive the media stream. However, ICE by itself is also vulnerable to attack. One example is the signal information used in ICE. The signaling information is vulnerable to unauthorized access or third-party modification. This can potentially allow an attacker to see the media being played by a user. In order to protect against this type of attack, ICE must rely on transport layer security. TSL will provide the encryption of these signaling messages through symmetric keys so that only the two intended parties will have the access to the actual data. Modern networks are constantly using NAT to divide the limited number of available public IP addresses, so establishing a connection through this NAT must be addressed. Therefore, the use of ICE as a means of NAT traversal is essentially today's network. The new version of RTSP can incorporate ICE to establish its connection for media streaming between the client and the RTSP server. ICE has the added benefit of security for attackers. ICE also allows NAT traversal regardless of the type of NAT, which further increase security as the user is not forced to lower their network settings for RTSP to work. The added benefit of reliability, usability, robustness, and security for incorporating ICE onto RTSP protocol will surely improve RTSP for the better and further increase RTSP's adoption rate. Thank you for watching. So by now you should understand the 4 different kinds of NAT and then the new method of a NAT traversal that is suggested to solve the issue of allowing users to use the RTSP even when the router running NAT is being used. So if you have any more questions, please do not hesitate to ask me. Thank you.